This is the East River Tunnel construction project of 1903 in New York. The construction commenced in 1903 and the tubes were completed by the 1907s. But due to the lack of knowledge of modern-day soil and rock mechanics and the lack of extensive site investigations, the project faced various construction accidents and some engineering errors that required part of the tunnels to be rebuilt. Some segments of the tunnels were sinking into the marine clay. This forced the engineers to drill some micropiles to underpin the tunnels and keep them in position. Fast forward to today. With all of our technological capabilities, subway construction is still regarded, for lack of a better word, risky business. However, the demand for these complex projects is only getting higher. The United Nations is projecting that the urban population will reach 60% of the world's population by 2030. So we can see with the increase of this urban population, the demand for public infrastructure is going to explode. In order to cater for these demands, there's going to be high need of these underground infrastructure. My name is Clemens. Today I'll be talking about the roles played by geotechnical engineers in the design and construction of subway systems. And this is Geotechs with Clemens. Let's get right into it. Subway construction projects are long-term projects. A single project can take years, if not decades, from planning, making the designs necessary, acquiring the necessary documents from the government, and raising the funds. Usually these projects are financed by public and private funds, or combination of the two. The construction of a mile-long subway line costs around $250 million to a whopping $1 billion. One thing to keep in mind about these projects is they don't happen in a vacuum. They involve the collaboration of different entities spanning from government ministries, design companies, contractors, legal teams to handle the contractual agreements. These projects are long-term projects and they are usually divided into 4 phases. Geotechnical engineers are heavily involved in all subway construction project phases. The importance of geotechnical engineers is to understand the ground conditions, provide safe designs, and providing construction sequence reports. Another reason is geotechnical engineers have to make sure that they preserve the surface, public and private infrastructure during and after the construction of the subway. Another thing to note is geotechnical investigations are iterative processes throughout the project cycle. For example, you can go up to phase 4, which is the construction phase, and you have to go back to phase 3 because you have to correct some of the documents or you have come across some unexpected geologic conditions. Phase number 1 is called the planning phase. This is where geotechnical engineers do the desktop study or the review process. So this is when engineers sit down and they develop conceptual geologic or geotechnical models. That is producing some cross sections and preliminarily identify some technical constraints and issues that might arise in the project. Moreover, in this phase, this is when geotechnical engineers plan subsurface investigation programs. So in the second phase, which is known as the preliminary or the feasibility design stage, this is where geotechnical engineers initiate field investigations, implementing the field drilling, for example, the CPT test, which is known as the cone penetration test, and collect samples and do some laboratory testing programs. The scope of this phase can often change based on the findings during the investigation. For example, if the geotechnical engineers come across some uncertainties or something that wasn't foreseen in the past and it needs to use a different type of equipment, that might usually take some time to acquire from a contractor or a third party. During this phase, this is often where the bulk of the site characterization effort is applied to make sure that they create the closest representation documents of the construction site. Phase 3 of the project cycle is called the final design, with some additional or follow-up field investigations. So in this phase, usually targeted specific geological or geotechnical features or issues that may impact the project design are the ones which are usually focused on. Geotechnical engineers have to produce geotechnical reports, that is, the data reports, design reports, and baseline reports that are required to initiate the construction of the project. But the interesting thing is the actual conditions to define the site and the engineering parameters, groundwater, and the ground behavior will be evaluated during the final phase. Surprises are inevitable. There will always be unexpected ground conditions, and neither the owner or the design team can completely eliminate surprises from the complex underground projects. This is a quote from Gaudi in 1995. With that quote in mind, the construction phase of the subway tunnel is the most challenging part. In this phase, we are talking about the logistics, monitoring, and facing unforeseen challenges that may dramatically slow down the progress of the project. To give you a better perspective and understanding of the construction phase, we can look at a construction project of Line 1 of the Naples underground subway system. This subway line is 30 kilometers long, consisting of 25 stations transporting 500,000 people a day. The route was constructed in a densely built urban environment with historic and artistic buildings that should be preserved at all costs. Some of the greatest drawbacks of the project was the fact that the line was well below the groundwater table. In order for geotechnical engineers to tackle the problem caused by high pore water pressure, the contractor adopted the closed-shield earth pressure balance machine to bore the tunnels. As for the stations along the route, they had a maximum depth between 35 and 50 meters below ground level. They were constructed using excavation method within a 1 meter thick reinforced concrete diaphragm walls, supported by steel tubular probes at the surface and a lot of several pre-stressed anchors to stabilize the retaining walls from collapsing. Due to the closely located buildings around the construction site, it was highly important to minimize movement of the station diaphragm box and to reduce the potential settlement of the adjacent buildings. Geotechnical engineers had to install multiple real-time measuring instruments to monitor any distortions in the retaining wall and ground settlement. In order to construct the platform tunnels and the connecting passageways, the construction was carried out with the aid of artificial ground freezing to create an impermeable collar parallel to the tunnel length. The frozen collar serves a static purpose for the inclined tunnel and waterproofing purposes for both the platform tunnels and passageways, providing a safe working environment and minimizing water ingression. In order to make future predictions of the construction project, a numerical analysis had to be implemented. Numerical analysis for such complex projects have a high computational cost, and geotechnical engineers have to know exactly how to use these numerical analysis softwares. There are many factors that geotechnical engineers have to put into considerations. For example, in order to have accurate numerical predictions of the ground movements associated with the excavation, the choice of an adequate constitutive model to represent the soil mechanical behavior is really important. Furthermore, there should be a correct definition of the soil profile. This comes back to the data which was collected during site investigation. The geotechnical engineers should have a clear understanding of the groundwater conditions and the initial stress rate of the soil. Moreover, the representation of the structural geometry and the boundary conditions should be implemented appropriately, and the modeling of the sequence of the construction phase must be feasible. In this project, the soil was assumed to behave like a linear elastic and perfectly plastic material with a Moore-Coulomb failure criterion, whereas the diaphragm was modeled as a linear elastic solid. The numerical simulation provided the project crew with a better idea of what to expect during construction and provided the benchmark values for the surrounding building settlement. It's one thing to use public infrastructure, and it's another thing to take a look and appreciate the work and the cooperation put forward to see through these amazing projects. With that, I would like to thank you for sticking around to the end of this video. Please do like, subscribe, and leave a comment down below.